Hello, once again, we are back. In this session, I will go through an overview about our course, which is going to be covered on the second midterm. Actually, we have contents from the first midterm too, plus the Mid2 model matrix, mainly the linear transformations and vector spaces. These are the topics that are going to be involved in the coming exam. Okay, let's remember together the first one, which the matrices properties. So I want you to go through the multiplication once more, just in a quick multiplication, addition properties, the transposition, the main properties of this part. This is really, very important. Also, you have that if I have a times a times a, you will have a to the power of k, which means if I needed to have a to the power of 2 just in case, I will get just only two matrices multiplied in each other. We usually call this idempotent matrix. And you have also for a equal to 0, which it's going to be the unit matrix. I want you to remember that not all the matrices are invertible, of course. All of you know that for the time being. But just to stress on this matter, the multiplication, of course, is not commutative in matrices, and simply like the inversion of matrices, except if you multiply a times b, it's exactly the same like b times a, and the result will be I. Once you have something like this, it means b equal to the inverse of a matrix. You can't get an inverse for a singular matrix. Do you remember what's the singular matrices?
Basically one.
The singular matrices are those matrices which their determinants doesn't equal to 0. So for any matrix with a determinant equal to 0, you can't get the inverse of this matrix. I will go through the properties of determinants shortly in these slides, inshallah. Okay, what's an elementary matrix? We already in the previous session, so the elementary matrices are the type or the form from the unit matrix, which is responsible about just interchanging rows, multiplying row by a number, multiplying a row by a number, then adding it on another row. Okay. Also, I want to go with you through these properties. If I have m matrix and times nm matrix, so the result will be mr by s. If I have mr to the power of s, the multiplication will lead to m to the power of r of s. A is invertible, the inverse of an inverse will lead to the main matrix. Okay. If AB is invertible, remark this, and you have A times B to the power of -1, it means B minus 1 times A minus 1. And we already did go through this in the previous examples. Once we have the B matrix, we just saw example like this, and we need to get the A matrix, so we will reverse the operations of multiplication. K times A is invertible, and the Ka minus 1 will equal to K minus 1 times A minus 1, when K is just only a scalar. So if you can take just a common factor from all the elements of the matrix, can go outside to K minus 1. A to the power of T is invertible. It means that A transpose minus 1 equal A minus 1, then you get its transpose. Both of them are exactly the same. Each elementary matrix is invertible, and its inverse is an elementary matrix, and we already did saw that in the previous slides. This is the slide mainly that's stating if you do some elementary matrices on A and it reached I, those matrices with this order in the A minus 1. You know that. And if I want to get the A matrix from an I, and I have these matrices, I will just get the inverse of these matrices times A, and I will be able to get A once more. So A minus 1, it equals to these elementary processes. And vice versa if you like to get A. This is actually the process that invented Gauss-Jordan steps, that when you put A matrix, you put unit matrix, and you start doing the reduced echelon form on A, you will find the inverse on the other side. Do you remember that? Okay. Rank of a matrix equal to A. What we mean about the rank? The rank the number of non-zero rows in the reduced echelon form, or in the echelon form. The reduced echelon form from A is the identity matrix. A is invertible. A can be written as a product of elementary matrices. The system AX equal to B is consistent, independent for every B belongs to R of M. This was just a quick refresher about matrices. If you remember what we mean about linear transform, linear transformation is really very simple. You will find how it is connected between the multiplication of matrices, the linear transformation, and a solution of a system of equation, and finally in vector spaces. We just saw by the end of vector spaces how to get the null. We already know that for a linear transformation, all we have to do is to get the transformation matrix times the vector x, and this is what we called the transform from Rn up to Rn. Not every transform is reversible. The reversible transforms are those ones with a matrix that can be inverted. So I can move from Rn up to Rm and vice versa, of course. Okay, for any linear transform, we know the kernel. Do you remember the kernel? It's the null of A. We just talked about it. So the kernel of the transform denoted by Kerti is the set of vectors in Rn which are mapped into the zero. And this makes a reflection. If I have Ax equal to 0, this is what's called the null of A, yes? Mm-hmm. So here's the link between of them. You already, that link started from the linear transform. Okay? The range of T, denoted by range T, is the set of images through T of vectors in Rn. And also, it's exactly like the result of multiplying A times X, which is given later on vector spaces. So range of T, it is the set of T of X such that X belongs to Rn and it's a subset of Rn. A linear transformation on the following conditions is called. Do you remember this? For any transform, it is admitting the addition process and the multiplication by scalar, we call it vector space. So already, if you have a linear transformation, space for linear transformation, admitting the two processes, which is addition for any two vectors under this vector space, and the multiplication by scalar, it will develop a vector space. So it is already linked a little bit with starting from linear transformations. Okay. Very good. And also, the T of 0 equal to 0, which addresses that the linear transform is actually a vector space, okay? Or sub-vector space from whatever the dimension of the space that you are dealing with. You have the three operations: existence of a 0, admitting closure under addition, and the closure under multiplication by scalar. Okay. Also, a linear transformation, remember, it can be written as A times x1, x2, xn, which can be extended to a linear combination from vectors through the coordinates which are x1 and x2 and xn. Voila! So actually the definitions that we've just taken in vector spaces already exist in the chapter of linear transformation. Are you with me, Fras? Do you remember all of this? Okay, so now I can state that A transform times x1, this is the standard basis of the vector space, yes? This is the standard basis of any vector space, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. If we are talking for R3, for example, if you have dimensions bigger than that, you will have the column with 1 at the number of relative to the order of this row, yes? Okay. Also, a linear transformation is completely determined by the images of the columns and of the identity matrix. Here is stating that linear transformation Rn to Rm and the inverse is invertible if and only if n equal to n. And if you remember the last problem in the previous exercise, we couldn't get an inverse transform because it was not a square matrix. Do you remember?
Yes.
Okay. And the matrix AT is invertible. And this is the case as I told you about. Now let's go for length of input and output matrix. Of course, all of these chapters are expressed and explained in plenty in more than one video regarding each one of them. We solved problems on each part of them. So please, once you are trying to review this part, just go through each chapter and try to solve at least the problems which are solved in the videos which we did go through it together. Okay, if you remember the length of matrix, which is the input and the output matrix, it's the economical matrix that connecting the amount of production, which is equal to the intermediate demand plus the final demand. What we mean about the intermediate demand, the amount of production that will be exhausted through the other branches or vectors or identities of your economy, okay, if you remember. And it can be represented by X equal AX plus D, where A, it's called the technical coefficient matrix, which bond the production and the amount, the relative amounts that exhausted in each category or in each aspect of your economical system. And finally, you will have the D. If I moved AX to the other side, of course, the elements of A is the production of sector I used in the production of sector J divided by the production of the sector. You have plenty of problems. A wonderful example of an economical system with three sectors, if you remember, the agriculture, the manufacturing, and the last one is the services, how they are connected together. You have everything in this video. Please go through it. Also, if I want to get the inverse length of matrix, which is simply just moving AX to the other side, taking X as a common, you will have I minus A, multiplying both sides by the inverse, you will get this form, which will supply you by the production needed if you have certain column of demand. Okay, so if you have the demand now, you can expect the amount of production required relative to each sector from the economical sectors, various economical sectors that exist in your economical system. Okay, this is called the inverse length of matrix. I want you to remember the name, of course. Also, the effect on the whole economy. For example, if you remember the inverse length of matrix, if it was given to you, and if I want to see the effect of an increase of 1 unit from any of the sectors on the overall production of a system, I can do this simply, just by multiplying the inverse of the length of matrix times D, which is, if you are just discussing or thinking about increasing just only 1 unit in sector 1, sector 2, sector 3, you can simply just insert the demand column, 100, so multiplying the inverse length of matrix by 100, it will give you the production of the sector 1 or the increase in production of sector 1. If you add these values all together, the values of the production, it will give you the increase of production relative to just only 1 unit from one of the sectors that already exist in your economy. You can do this for the second, for good number 2 or for good number 3, and also you can compare which one of them will have a greater effect on your economical system just going through this. I want you to go through them. It's really full of everything. So now this is related to the previous slide. We'll see that the highest effect, I believe, will happen with just increasing the demand on good number 1. And this is also explained in details in your main lectures about this part of the length of matrix. Finally, we are talking about vector spaces, which is the last chapter. It was not covered within the first midterm. So mainly for the second midterm, I want you to concentrate with vector spaces. You will have a couple of questions from previously, but also I will need you to go through this. Remember, what's a vector space? Vector space is not an empty set of vectors. These vectors must be a closure under addition, and this is if you have just only two vectors, and the addition will belongs to the same vector space. It's derivative phenomena, commutative, the existence of a zero of V, and the similarity of any vector. Then this closure under multiplication of vectors, and all of these are the conditions to have a vector space in order to have a vector subspace. Also the closure, additive closure, and the multiplication by scalar closure. But with them, don't you ever forget that any subvector space should share the origin, or should share the null vector with the vector space. This is mainly the main condition to have a subvector space. And also, any vector space is a subset from itself. And any subvector space can be looked at a vector space by itself. Okay, if you have U1 and U2, and you have the addition of U1 and U2, these comments are really very important. Through the main session of this part, we just go through them quickly. But I've added here a couple of slides explaining exactly what's happening, or the differences between addition and intersection, and finally union of two sub-vector spaces from a general vector space. For us, bottom line, if you have just only two sub-vector spaces and you are adding them on each other, the composition of the new vector set, it's gonna be apart from U1 and U2. So actually, you will have a new and a bigger set of vectors, Mr. Franz. See, I am adding the elements of X and Y relative to U1 and U2. So actually, I'm building a new structure, which is a combination between X and Y vectors, where X belongs to U and Y belongs to Y2. The intersection, and this is why it's also a vector subspace of V. So the addition process will develop, the addition process of two subvectors, it will develop mainly a new subvector space, which is apart from the vector space that you are initiating. The intersection, which means that you are getting both of the shared subvectors vectors that exist in these two subvectors. And since each one of them is a subvector space from the general vector space, so each one of them contains the origin, so the intersection will lead to a set of vectors, which are also a subvector of the vector space. But for the addition, it's not a must, because you are adding elements from U1 and the elements plus, the vectors from U1 or the vectors from U2. That's what we mean about union. This is why I've inserted these couple of slides, and I've sent it all to you. Okay, the first of them is talking about the intersection. Once I have subvector space A intersection subvector space B, it's going to be the set of vectors which belongs to both A and B at the same time. And this is going to be a subvector space. This is the bottom line. The intersection will develop a subvector space from any vector space. This is in details explaining to you what we mean about intersections and the main probabilities that intersection always produces a subvector, as I told you. A and B are vector spaces or subvector spaces, then their intersection is also a vector subspace. An intersection can be empty if there are no common elements between the two vector sets. For example, if I have A, which is a subvector space, the bases of A are 1, 0, and 2, and 0. And for B, the main vector space which is 1, 0, 3, and 0. So the intersection will have the form of 1 and 0. معايا في راس؟ يبقى إذا ده for intersection. If we are talking about addition, remark the huge change. In addition, for us, be with me. In addition of two sub-vector spaces, you will develop a new vector space. This example, okay, let me just jump to this example. Look at this example. It states that I have a vector space A, sub-vector space, which is simply with the basis of 1 and 0. تعرف يعني ايه 1 and 0؟ البيسس يعني set of vectors كلهم 1 و 0. يعني بتضرب K في 1 و 0 يعني 2 0 3 0 4 0 negative 2 0 negative 1 and 1000 and 0 and so on. All the images on the form of something in X and 0 in Y. Once you add this set to this set, you will have a new set, which is 1 and 1. So actually, the structure of the vectors are changing. These are the vectors, that position vectors, which belongs to the x-axis. Those are the position vectors which belong to the y-axis. Once you add them together, you will get 1, 0, 0, 1. Once you add them, you will get 1 and 1, which represent the whole plan, the whole R2. So, bottom line, in intersection, we are interested in the common vectors between two subvector spaces.
Okay.
In addition, you will have a bigger vector space that admits or contains the first set, the second set, and the new set, which constructed from the elements that's shared, that's going to be built from both of these two subvectors. Do you read me? Okay. This is, of course, as I told you, this is the last expression. However, if we are dealing with entire subspace like R2, the sum of two subspaces could result in a larger subspace, e.g. R2. So here we were talking about the position vector of X and Y, but when you add them together, you will get the whole plan. While in union, you are taking all the elements literally in A or all the elements in B without changing the vector structure between them. It's just simply I'm going to gather all the elements from the x-axis, all the elements from the y-axis. There is no other shared elements. And there is a proof that this union may not be develop a sub-vector space. تعال بص كده. لو أنا ضربت المثال اللي فات, if we just go through the previous example, just wait a second. Okay? Yes. Look to this example. I'm having exactly the same example. Here I have 1, 0, and B is 0 and 1. So if you are talking about union, I will take all the images from 1, 0 and all the images of 0 and 1. This set of vectors represent a vector space? Let us check. The first thing from vector spaces is to be the closure under addition, yes?
Okay.
If I added these two vectors, what's going to be the result? If this type of vector already exists in this set?
Yes.
No.
Yes.
This set contains only the images of 1 and 0, or the images of 0 and 1, but it doesn't contain a vector with the addition, combination between them.
Okay, sure.
Okay? Sure. Do you understand me?
Yes.
So you have a failure in the, as I told you, in the union, it's not closed under addition, so it's not a subvector space. This is the summary. The section focus on the common elements. Union combines all the elements from both sets without any addition of vectors, but in the addition of subvector spaces, there will be an addition of vectors, so you will have another vector space. So mainly for intersection and addition, you will have subvector spaces, but for union, you are not chosen. Okay, here is a comparison between intersection, union, and addition. It's already written and I've sent it to you, containing everything from the definition, the result, the operation, the resultant set, the subsets, and the closure under the addition. Already we did go through it. Now, Let's get back again for the vector spaces. Do you remember the linear combination? What's a linear combination? That I can get any vectors from the vector space as a linear combination from the set of vectors that exist in this vector space. Okay? So this is mainly what's the linear combination, getting a combination between the vectors and the coefficients, which are K1 and K2. This is going to be advanced more once we talk about the span, which is the set of all linear combination, which is the whole set of linear combination of certain vectors, is called the span. يبقى ايه السبان؟ set من الvectors that with certain combination will develop any vector that belong to the vector space. معايا انا؟ اوكي؟ but هنا مفيش condition انهم يبقوا linearly dependent. هي الست دي ممكن انك انت to combine it together in order to get مين؟ to get V. فاهم معنى كلامي؟ اوكي. خلي بالك the set of all linear combination is called the span of V1 up to Vn and denoted as the span of vectors that's generated or the generators of vector space. Okay? Or a set of vectors U1 or U2. So once more, if S is the span from V1 up to Vn, it's said that V1 up to Vm generates S, or S is generated by this set of vectors. Okay? Perfect. So if V1 are vectors of vector space V, then the span is V1 up to Vn is a vector subspace, is also a vector subspace of V. Okay, the solution set of a system of linear equation is a vector space if and only if the system is homogeneous. Stop. ليه? Why? تاني, a solution set for a system of equation is a linear subspace. ليه؟ لأن كده هيدي لك infinite number of solutions. والinfinite number of solutions we get some of the variables as a function in the remaining ones, which develops that you don't have one solution. صح يا فراس؟ يبقى عندك كمية كبيرة من السولوشنز. كل دول will depend on the value of the chosen unknown. And these values will develop out of vectors. صح؟ These vectors are called vector space. It can be a vector space. So once more, let's read it. The solution set of a system of linear equation is by itself a vector space if and only if you are solving what? Homogeneous solution. Let's remember what's linearly independent and what's linearly dependent vector set. When, if you have a set of vectors, you can call them independent or dependent. Simply, if you have V1 up to Vn multiplied by K1 up to Kn equal to 0, and the only thing that will make this right-hand side, left-hand side equal to 0 is to have K1 up to Kn equal to 0. يعني معناها فرص لو انا جبت مجموعه من الفيكتورز عايز اشوفهم linearly independent او لا، اخد الست دي ماشي واوجد الفاليوز احاول to solve reduced echelon form. If I got a unique solution يبقى linearly independent. طب if you got a dependent solution يبقى linearly dependent. حتى اسمه ايه؟ infinite number of solutions. Yeah. Some of them will depend on the others. Okay? So the vectors to be independent, you will have to get a unique solution, which is the trivial solution, that all the vectors or all the k's are equal to 0. Otherwise, they will be dependent. معايا ده واضح؟ Okay. V be a vector space, all subset of V, just one non-zero vectors is linearly independent. Okay. Consider V1 up to Vn and let A be the matrix which columns corresponds to the vectors. دي الماتريكس اللي انا كنت بشتغل عليها through the previous lectures اللي هي بسميها ال A matrix اللي كان الفيكتورز بتوعها السبان باخدهم بحطهم as columns. دي اللي بقدر اجيب لها null او null space او row space او column space. Yes? Okay. Perfect. A set of vectors of Rm is linearly dependent if and only if one of the vector is a linear combination of the other. يبقى لو اديتك set of vectors لقيت واحد فيهم can formed from the other two vectors by linear combination يبقى dependent set of vectors. وده بيردني بعد كده للبيزس. What's the condition of a basis for a vector space? What's the condition? To have a set of vectors which are number one linearly independent. Number two, they can form any vector in this vector space. ده اللي بسميه البيزس. تاني، يعني ايه البيزس؟ يعني مجموعة الفيكتورز اللي جنريت الفيكتور سبيس ده. عددهم اوبتيمال، ده الاوبتيمال اللي يطلع الفيكتورز اللي موجودة هنا. لازم الست بتاعت الفيكتورز دول رقم واحد يبقوا linearly independent. رقم اثنين literally they can form any vector within this vector space. The simplest example on the basis are the standard basis, which is 1001 for R2. You using these set of vectors, you can literally develop any vector that belongs to R2. Similarly, like R3, 100, 010, 001. You can combine them together with any combination to get any vector that belongs to me to R3. معايا فراس فاهم انا بقول ايه؟ اوكي. انزل عندك proposition a linearly independent set of vectors of Rn form a basis for Rn. Let V be a vector space, A, B, B, C are basis for V. Then B and C have the same cardinality. لو انت عندك two bases يبقى الاثنين bases دول لهم نفس المصداقيه في الفورميشن بتاع اي coordinate بتاع اي vectors. What's the dimension of vector space? Dimension of vector space is the number of vectors in basis. عدد الفيكتورز اللي موجوده فين؟ في البيزس بتاعك. اوكي؟ dimension V is the number of vectors in the basis of V. Let V be a vector space. UV belongs to the vector space, two sub-vector spaces, I'm sorry. So you have the dimension of U equal dimension of W, and U is a subset of W, then both of them are the same, they are identical. Also, let V be a vector space. By convention, we say that the empty set is the basis for the zero, which is the empty set, and the dimension vector is equal to 0. Dimension of Rn equal to n, which represent the number of vectors that exist in the basis of Rn. For a matrix m by n, so the dimension is m times 2. The standard basis, if you remember, once more, for R2 are 1001, and for R3 are 100, 010, 00, and 1. And for n and we call them the standard basis and also the canonical basis. Let V be a vector space and the beta a basis for V. So V belongs to V. There is only one linear combination of the vectors in V which equal to V. Here's the state of the coordinates. What are the coordinates? The coordinates are the set of combinations that once you use them with the vector space, the main basis, vector basis, you will get any vector in this vector space. يبقى الكوردينتس هم الكوفيشنتس C1 C2 CN. ده اللي احنا بدأنا بيه، كنت انا راجعت عليه النهارده الصبح، اتكلمت عنه كتير قوي النهارده. The coordinates can be written simply. The coordinates of vector U with respect to the vector space B are C1, C2, C3, Cn, which means those coordinates. Okay. For example, if I have B 1, 2, 3, 4, 5, 6, 7, 8, and 10 basis for R3. If I want to get the coordinates, لو أنا عايز أجيب vector, I'm sorry, if I want to get a vector, and I know, and we know the coordinates, all I have to do is to write this vector as a column. This is the second column of the matrix, that's the third one. Multiplying this matrix by this coordinates, it will give you the vector that you are interested in. Once you get the vector, see, here is the vector, which is 16, 20, 25. It's exactly similar, like get the coordinates of this vector with respect to the standard form. فراس المعنى اللي بقوله دلوقتي ده مهم قوي. من الآخر أنا لو اديت لك البيزس واديت لك الكوردينتس تقدر تحطهم على بعض وتجيب الفيكتور، صح؟ إزاي؟ هفتح ماتريكس احط فيها الفيكتورز بتاعت البيزس as columns، بعدين اعملها مالتيبليكيشن في الكوردينتس هتديني الفيكتور بتاعي. بس خلي بالك ان اي فيكتور whatsoever I can simply define it or find the coordinates بتاعته بالنسبه للستاندرد بيزس. ليه؟ لان الفيكتور مثلا 16 و20 و15 دي الكوردينتس بتاعت دي ارقام الفيكتور، صح كده؟
اوكي.
هم بالكوردينتس لو انت بتتكلم عن الستاندرد بيزس، لان ده هيبقى 16 في 100، ده هيبقى 20 في 010، ده هيبقى 25 في 001. لذلك لو جيت تقرا هنا بيقول what are the coordinates of u، دي coordinates with respect to the canonical basis. لما اسالك هنا دماغك هيروح على coordinates، لكن هو دماغك المفروض يروح لمين؟ للفيكتور. الفيكتور اللي بيبقى فورمد من مين؟ من الكوردينتس اللي موجوده قدامك. معايا حبيبي؟ اوكي. طيب العكس، انا ممكن اديك الفيكتور واطلب منك الكوردينتس، لان simply I want you to remember in all times that this is the A matrix which is got from the basis of a vector space. This is X, which stands for the coordinates of any vector, and the result will be the vector by itself. So if I want to get a vector, all I have to do is to get the A matrix from the basis multiplied by the coordinates, okay, and I will get a vector. If I want to get the coordinates, I can multiply any vector by the inverse of A, okay? أو أحل جاوز جوردن أو مطلع الكوردينتس، وده اللي موجود عندك في السلايد، ده مهم جدا. اوكي؟ طبعا دي الايديا بتاعته موجوده معاك. العكس هنا you are given the vector and I want to get the coefficients. So C1 times the first vector, C2 times second, C3 times the third vector, which equal to 12, 15, and 19. I will solve this either by Gauss-Jordan, because it's a system of equations, or simply get the inverse of the matrix which is responsible about changing the basis multiplied by the vector, and I will get the coordinates. Same way like in these couple of slides, it's exactly the same. Now I'm talking about the orthogonality. Okay, you came today at this point. How to know if you have two vectors are orthogonal? Simply, if you get the multiplication of both of them and the result will equal to 0. This is what we call an arc or row column spaces, and it's stating that the orthogonal complement of vector on any vector space is also a sub-vector space. Here is written for the orthogonal complement of any subset of vectors. I want you also to remember the determinant of a matrix. This part, I went through it by the